So this is Pulleys 6. This video covers a pulley system with one mass hanging vertically and one mass resting on a smooth incline. So just get straight into the problem. So example 6, two masses A and B are connected by a light inextensible string that is passed over a smooth fixed pulley. Mass A hangs vertically below the pulley and mass B rests on a smooth plane inclined to an angle of 35 degrees. We'll just draw out that much so far. So there's an incline of 35 degrees, and that will always be to the horizontal. Mass A hangs vertically below the pulley, so mass A must hang here. Mass B rests on a smooth plane, smooth meaning we won't have to consider friction. So we can place B here. They're both connected via a string. Masses A and B are 2.3 kilograms and 3.2 kilograms respectively. Okay. As with all of these questions, regardless of what's asked, regardless of what's specified in parts A, B and C, we should go through at least steps 2 and 3. So step 2 will be to put the forces on. So the forces acting on the 2.3 kilogram mass or its weight, 2.3 G, and tension, which acts up. Tension always acts away from the object it's connected to. And then we'll put tension onto the 3.2 kilogram mass, and then we'll put its weight on, remembering that weight always acts straight down. So that's 3.2 G. Okay. And then we should put on the acceleration arrow, step 3. Here it's actually a little difficult to tell which way the system will slip, so we just have to pick a direction and make sure it's consistent. So by consistent, so this is consistent because if the 2.3 kilogram mass accelerates down, then the 3.2 must accelerate up the slope. It's just as reasonable to reverse the accelerations and have up for the 2.3 and down for the 3.2. But we've picked one, we stick with it. Then we'll apply, so to deal with part A, calculate the acceleration. Well, acceleration, we bring this in by considering ma, so we have to do step 4, which is apply Newton's second law, F equals ma. We'll apply this to the 2.3 kilogram object first. It's accelerating down, so we'll take down to be positive. So 2.3 G minus T is equal to 2.3 A. Okay. Then we apply the same process to the 3.2 kilogram mass. This one accelerates along the slope, so we'll make our acceleration, our positive direction, up along the slope. So tension is definitely acting up along the slope. For the next bit, if we look at the weight actually acts straight down. It's not aligned with this direction up the slope. So we need to break weight down into relevant components, into the slope and along the slope. Along the slope, this component down here, that's parallel to the direction we're considering, so that's a relevant component. The angle of inclination is always the same as the angle that goes up in the top corner of this triangle here. This side here is the opposite for this triangle, referring to that. So if it's opposite, we need to use sine. So this would be 3.2 G, the full force, times by sine 35. And that's equal to 3.2 A. It's easier to use elimination to deal with these equations. It gets rid of t right away, and we can answer part A and get acceleration. So if we put equations 1 and 2 together by adding them, we'll end up with 2.3g minus 3.2g sine 35 being equal to 5.5a. If we rearrange that, that will be 2.3g minus 3.2g sine 35 divided by 5.5. And that makes the acceleration 0.828 meters per second squared. Okay. Fine. And then in part B, calculate the tension in the string. Well, if we look back at these simultaneous equations, we can actually see this is fairly easy to do. T and A were the two things that were missing in those equations. We found one of them. Simultaneous equations are always much easier to deal with once you found one of the variables. So we just pick one of the equations. So let's pick equation 1, just because it has no trig in it. You could rewrite that as 2.3g minus a is equal to t, and that will give us 20.64. So we've got tension, that's part B. And then C, calculate how far up the slope B will travel. So as A falls down, B, the 3.2 kilogram object, will slide up the slope like that. The question is, how far will it go? So we're told that mass A was originally 2.2 meters above the ground, and B is a long way from the pulley. Saying B is a long way from the pulley basically means that object B will never be stopped by running into the pulley. It's just subject to the forces that act on it. So we know it must travel at least, so B must travel at least 2.2 meters, because that's the distance A falls. But at the end of those 2.2 meters, B must have picked up some speed, and as a result it will continue to slide up the slope until it's brought to rest. But B will continue to slide up the slope until it's brought to rest. So we need to think about that. So let's consider, so this is a question about distances travelled, so we should set up a suvat. And we'll set this suvat up for the case when the string has gone slack, so when A's already hit the ground and B's picked up some speed. So slack string. So we don't know how far it goes while the string's slack, we need to work that out. We don't know how fast it's travelling. We know that by the end, when it's travelled its maximum distance, B must stop instantaneously. We don't know its acceleration, and we don't know the time it travels for. So we know almost nothing there. So we should consider another suvat. So while there is tension, so suvat. So while there is tension, B travels 2.2 meters up the slope, taking up the slope to be positive. It starts from rest. Its final speed we don't know, but we do want to know, because whatever speed it finishes this stage with is the speed that it starts the next stage with. So that would give us u when the string is slack. The acceleration we do know, that was worked out in part A there. So that's 0.828. And then the time that this runs for, we neither know nor care about. We need to use the equation that doesn't have t in it in order to work out v. So we use v squared equals u squared plus 2as. So v squared equals 0 squared plus 2 times 0.828 multiplied by 2.2. Therefore v is equal to 1.908 meters per second. It's always easier just to update your SUVAT instead of having to look at your SUVAT and search the new information that you have. So we'll update wherever it goes. We still have a problem over here with this SUVAT in that we only know 2 pieces of information. We only have 2 pieces of information, so we need a third. One key point is that acceleration can always be found by considering forces. So let's do that. So B is sliding up the slope with some speed. In this case there's no tension because A's hit the ground and the string has gone slack. So the only forces acting on it would be the reaction force and its weight, so that's 3.2 g. If weight's the only thing acting on something on a slope, it's definitely going to end up accelerating down or decelerating up, so the same thing. So if we know acceleration is directed down the slope, we should resolve down the slope. R doesn't partake in that because R is perpendicular to that, so it has no effect. Weight is vertical, so we need to break it down into its along the slope and into and out of the slope components. So we want this one here, the opposite, that's along the slope. That's 3.2 g sine 35. So 3.2 g sine 35. It's the only force or component acting, so it is equal to ma. We can cancel the m's, the 3.2's, and we know that a is equal to g sine 35, which is 5.621. So again, SUVAT should always be updated, this vertical SUVAT, just so that everything is easy to see. Now we have enough information in this SUVAT in order to find how far B travels. So we want the equation that doesn't have time in it, so again, v squared equals u squared plus 2as. V squared equals u squared plus 2as. So 0 equals 1.908 squared. And bear in mind that the acceleration was down the slope, so that actually should be negative just there. Minus 2 times 5.621. Multiplied by s, the distance we're trying to find. So s is 1.908 squared over 2 times 5.621. So that's 0.324 meters. How far up the slope B will travel? So we know it goes up by at least 2.2 meters, but then on top of that it travels another 0.324. So distance up the slope is 2.524, 2.52 meters. That's it.